Hello, and welcome to the series of lectures on number systems. In this series of lectures, we'll discuss about the different types of number systems, particularly those used in computer systems. To do that, we'll first begin with a number system that is very familiar to all of us, and we'll build on to the different types of number systems that are used in computers, and finally make a generalization that will allow us to develop a number system of our own liking. To do that, we need to be very familiar with the rules that govern a number system. For instance, consider a number system that is very familiar to all of us, the decimal number system. It takes its name from the Latin decim and from the Greek deca, both of them meaning 10. From this name, we can easily ascertain that this number system is formulated on 10 digits, starting from 0, 1, 2, going all the way up to 9. Notice that 10 is not a basic digit of this number system. In fact, we'll notice that all of the number systems begin with 0 and comprise of most, if not all of these digits, depending upon how big they are. Now, how do we form numbers using decimal number system? Because we know from real life that we are not restricted to just 9 numbers. We have billions of numbers, and we can form pretty much any number if we know the number of digits in it. So how do we do that? If you recall, in our elementary mathematics classes, we learned units or ones, tens, hundreds, thousands, 10,000s, and so on. These are known as the weight, or in singular, the weight of a number. Let's consider an example. Suppose we have the number 9257, and we know how to read this. It is read as 9,257, and we can actually write it in words. Now, writing like this, hopefully it will be obvious what weights mean and how they correspond to each of these digits and their respective position in this particular number. Now, if you write it column-wise, it will come up to something like this. Essentially, what this means is that we take 9 thousands, then add to them 2 hundreds, 5 tens, and 7 ones. This is essentially how we form any decimal number. We just multiply the number with its respective weight. This becomes 9 thousands, 2 hundreds, 5 tens, because 5 tens are 50, and 7 ones. And you can make any possible number in the same way. So if I want to make a number like 300,357, I will multiply the appropriate digits with the appropriate weights. Now let's get a bit mathematical. I can write 1000 as 10 times 10 times 10. Multiplying 10 together 3 times would actually give me 1000. Similarly, I know that 100 is formed by multiplying 2 tens together. 10 is simply 10, so we'll just bring it down like this, and for the time being, we'll just bring down 1 as it is. Now we'll use the concept of powers. 10 times 10 times 10 is another way of saying 10 cubed, or 10 raised to 3. Likewise, 10 times 10 is another way of saying 10 raised to 2, or 10 squared. 5 times 10 can also be written as 5 into 10 raised to 1, because 10 raised to 1 would actually give me the same number again. Now, if you remember how indices work, you know that any number raised to the power of 0 is actually 1. So I can raise 10 to the power of 0 to get 7 times 1. I hope you notice the pattern here. We start from the ones position with an index of 10 raised to 0, and then we keep on increasing the index as we move left towards increasing weights. Notice another pattern here. You see that every number is multiplied to the base of 10 raised to some power. This 10 comes from the decimal number system. So in fact, if you raise any digit of the decimal number system to 10 raised to its respective power, you'll get the value of that digit in terms of its weight. And this is pretty much how you would form any number in the decimal number system. You multiply it by 10 raised to its respective weight. Suppose I need to form a number like 1, 2, 3, 4, 5, 6. And this is actually 123,456. To see how I got this number, I will simply start from this point, which is the ones position, and move leftward in terms of increasing weights. And every time I would increase the weight by a factor of 10. So I'll start with 10 raised to 0, then 10 raised to 1, which is 10, then 10 raised to 2, which is 10 times 10, then 10 raised to 3, which is 10 times 10 times 10, and so on and so forth. So I can write this as 6 into 10 raised to 0 plus 5 into 10 raised to 1 plus 4 into 10 raised to 2 plus 3 into 10 raised to 3 plus 2 into 10 raised to 4 plus 1 to 10 raised to 5. And if I expand this, I will get this as 1 into into 5 zeros plus 2 into 10,000 plus 3 into 1,000 plus 400 plus 5 times 10 plus 6 times 1. And I will complete it over here. This would actually be equals to 100,000 plus 20,000 plus 3,000 plus 400 plus 50 plus 6. And if you add them all together, we'll get the original number 1, 2, 3, 4, 5, 6. And this is how you form any number in the decimal number system. So to sum up, the decimal number system makes up of 10 digits, starting from 0 all the way up to 9. And when forming a number in the decimal system, we multiply a digit by its respective weight. And the weight is given in the form of base 10 raised to some power, depending upon which position it falls in. Hence, this decimal number system is also known as a base 10 number system. Additionally, this 10 is what is known as a radix, and this radix essentially forms the base of any number system that we are going to deal with. It tells the number of digits that number system is comprised of. At the same time, it also tells the base with which we need to multiply that particular digit to obtain the weight of that digit. And it's easy to identify the base of any number system because essentially it will somehow be included in the name of that number system. Every digit in a number is assigned a weight based on its position, as we discussed earlier, and the weight is the value of that digit within that number. As I said, 9, 2, 5, 7, where 7 had the value of 1, 5 had the value of 10, 2 had the value of 100, and 9 had the value of 1000. Now, this is easy to calculate because this is a whole number. But what if we have a number such as 7.257? What do we do in that case? Whole numbers were easy because we just increase the power of 10 going left. We increase the weights in that way. But what about if we have a decimal number? In this case, what we do is we take the decimal point as the reference. This is also known as a radix point because it's used in the decimal number system. We call it a decimal point, but if you use some other number system, you can call it something else. But the technical term is the radix point. So we take the radix point as the reference, and everything towards the left of the radix point is treated as we treated the whole numbers. So 7 in this case has the weight of 10 raised to 0. So this is 7 into 10 raised to 0. That is, it has the weight of 1. But what about 2 and 5 and this 7? What are their values? Now, everything towards the right of the radix point or the decimal point is something that is very small. So we need to make its weight small as well. Now, if you consider 2, for instance, just this part, just 0.2, where I removed the 7 and removed everything after 2, we can actually see that it has a precision of 0.1. So I can essentially get this 0.2 by multiplying the digit 2 with 0.1. What about 5? If we remove everything else, we can actually see that 5 is of the precision 0.01. So we can get the 0.05 by multiplying it with 0.01. In the same way, we can get this 7, this one, by multiplying 7 with 0.001. If we try to bring these precisions, this 0.1, 0.01, 0.001, in terms of the indices, the base and its powers, 10 raised to some power, as we discussed earlier, how do we do that? Well, there's a simple way to do that. 0.1 is actually equals to 1 over 10. In the same way, 0.01 is actually equals to 1 over 100. And likewise, 0.001 is actually equals to 1 over 1000. Now, we already know how to write these 10, 100, and 1000 in terms of some power of 10. So we can actually write this as 1 over 10 raised to 1, 1 over 10 raised to 2, and 1 over 10 raised to 3. So if I rewrite this whole thing, I can say that everything to the right of the decimal point here, which is essentially 0.257, can be formed by multiplying 2 into 1 over 10 raised to 1 plus 5 multiplied by 1 over 100 or 1 over 10 raised to 2, adding it to 7 times 1 over 10 raised to 3. We form the pattern this way as well. Now, there's another mathematical concept that when we bring this particular term from the denominator to the numerator, we actually change the sign of this index. So 10 raised to 1 becomes 10 raised to minus 1, 10 raised to 2 becomes 10 raised to minus 2, and 10 raised to 3 becomes 10 raised to minus 3. So this term, this whole term, would actually become 2 times 10 raised to minus 1 plus 5 times 10 raised to minus 2 plus 7 times 10 raised to minus 3. And if you have more numbers after this, we have more digits after this, we'll keep on increasing this, 10 raised to minus 4, 10 raised to minus 5, until we need it, until the last digit. So you see the pattern here. Every time we move towards the right of the radix point, we multiply the digit by a negative power of 10. And we decrease those powers. We go from -1, -2, -3, and so on and so forth. And because if they are in negative, they're actually called decreasing powers. If I were to write this number in its respective weights, I can actually write it like this. 7.257 is actually equals to 7 times 10 raised to 0 plus 2 times 10 raised to -1 plus 5 times 10 raised to -2 plus 7 times 10 raised to -3. And this would actually turn out to be 7 plus 0.2 plus 0.05 plus 0.007, which will actually be equals to 7.257. This whole concept is summed up at this point. If we take the decimal point or the radix point as reference, we increase the powers to the left with 0 next to the decimal point, as we discussed in the case of whole numbers. Suppose 9257, where this was the decimal point because we can actually write it as 9257.00. So starting from the decimal point towards the left, we had 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3. We had increasing powers of 10. And towards the right of the decimal point, we have decreasing powers with -1 next to the decimal point. So we have 10 raised to -1 right next to the decimal point, 10 raised to -2, 10 raised to -3, and so on and so forth, depending upon the number of digits that we need. And because everything over here is in some power of 10, this number system is known as the base 10 number system. Now, how do we count this? This is something that is very intuitive, it's very trivial, and we all know it. But why is this important in this particular series of lectures is that if we know the concept behind counting in decimal, we can easily apply the same procedure to counting in any number system. And it will actually help in addition as well, because counting is just adding 1 to the digits. So let's see how we do it. Counting is simple. We start with 0, we move to 1, 2, 3, and we keep on going until we go to 9, and then we come to 10, and then we go to 11, 12, and all the way up to 99, and then we come to 100. How do we achieve these numbers? What is the concept behind it? Well, I can write 0 as 0, 0, 0, and these two are equivalent. Likewise, I can write 1 as 0, 0, 1. And this works. Why? Because this is 0 times 10 to the power of 2, which is the hundreds place, plus 0 into 10 raised to 1, which is tens place, plus 1 into 10 raised to 0. Now, any number multiplied by 0 is 0. So this has no value, and eating zeros has no value. So this actually becomes 1. Likewise, 2 becomes 0, 0, 2, 3 becomes 0, 0, 3, and so on until we get to 9, which is 0, 0, 9. So only the units place has been increased. We've now exhausted all of the digits. There's no digit beyond 9. So what do? We restart. We go back to 0. So the units place goes back to 0. But if you go back to 0, 0, 0, this messes up the count because we cannot count thousands or 1,000s or 1,257 anymore. So what do we do in this case? In the units place, because 9 is the maximum digit that can be used for a decimal number system, and it cannot go any further, the units place restarts from 0. And to make a meaningful number, we need to place something along with this units place so that we can increase the numbers beyond 9. Notice that the tens place so far had zeros, and what comes after 0 is 1. So once the units place has exhausted all the numbers, it has completed one entire cycle and goes back to 0, the next logical step is that the tens place goes from 0 to 1. Notice there's no change in the hundreds position because so far the tens position has not exhausted all its possible digits. So this is how we get 10, and this is why 10 is not included in the basic number, because it's not a basic number. It is not something that can alone represent a digit in the decimal number system. It is formed of digits having two different weights. That's why 10 is not included in the list of digits. This is how we get 10. And for the rest of the numbers, all the way up to 19, you can see that the tens position does not change, but the ones position, the units position, keeps changing, keeps incrementing. And once it has exhausted its limit, it has completed one more cycle, the next number is 0 at the units place, and the tens position is incremented from 1 to 2. It moves on to the next position, to the next digit. And this is how you get 20. And this is how you get 30, 40, 50, all the way up to 99. Now what happens at 99? At 99, the ones position has used up all of its digits. The tens position has also used up all of its digits. So what happens? 9 turns to 0 because ones position completes another cycle. The tens position completes a cycle, so this turns to 0. But if I add a 0 at the hundreds position, it's going to go back to this number, which is counterintuitive. So what happens, because so far the hundredth position was 0, the next step is that it will become 1. And this is how we get 100. And when we get to 199, the same thing happens again. The ones position becomes 0, the tens position becomes 0, they have completed their cycles, and because the tens position has now completed another cycle, once this cycle is completed, the hundreds position becomes 2, all the way up to 999, where all of these three have completed their cycle. In fact, what is important is that the hundreds position has completed one whole cycle, which makes this thousands position turn from 0 to 1. The rest of the digits become 0. And this is essentially how you count any system. You complete the cycle of digits in one position, in one weight, and once you've completed the cycle, when you restart it, the next weight, the subsequent weight, increments by 1. If you understand this concept, it will make it easier for you to understand how binary counting is done and how binary addition is done. This is the same thing that works in addition as well, because if we add 1 to 99, we get a 0 here and we get a carry here. And then we add 9 to 1 again, because again this is 0, we get 0 here and we get a carry here again. And because both of these digits are 0, we simply bring down the carry and we get 100. Addition is essentially counting. This is why it's very important to understand this concept of how counting is done. Suppose we have n digits. Let's suppose n equals 2. So we have 2 digits. So we know with 2 digits, we start off with 0, 0. We can make 10, we can make 20. We can go all the way up to 99. We cannot exceed 99. 99 is the maximum number that we can make when n is equals 2. Likewise, let's suppose n is equals 3. So we start off with 0, 0, 0. We can get 0, 0, 1. We can get 100. We can get 159. We can get 197, 777. We can even get 999. But that is the maximum number that we can get, because each of the units and tens and hundreds position has the maximum possible digit. It cannot exceed this, because the next digit will be 0, 0, 0 in each of these positions and the counting will restart. So 999 is the maximum possible number. Consider n is equals to 2. This n is actually the power of 10, 10 raised to n. So 10 raised to 2 is 100. Now 99 is 100 minus 1. So 10 raised to 2 minus 1, which is 100 minus 1, is actually equals to 99, which is the maximum number that can be formed by 2 digits. Now, if n equals 3, and n is the power of 10, so 10 raised to 3 is 1000, and 999 is 1000 minus 1. So 10 raised to 3 minus 1 is 999. We can form this maximum number with 3 digits. What about if n equals 4? What do you think the maximum number that we can form will be? Actually, n equals 4 means 10 raised to 4, which is actually equals to 10,000. But n equals 4 means that the maximum number that we can form is 9999, which is 10,000 minus 1. I hope you notice a pattern here. So the maximum number we can form with 4 digits is 10 raised to 4 minus 1. And this is how we form the formula. Maximum number that can be represented by n digits is 10 raised to n minus 1, where n is the number of digits. With 2 digits, n is equals to 2, we can form 10 raised to 2 minus 1, which is 99. That is the maximum number that we can form. With n equals 3, we can form 10 raised to 3 minus 1, which is 990, maximum number we can form. N equals 4, we can form 10 raised to 4 minus 1, which is 9999, the maximum number that we can form. And so on and so forth. In fact, with n equals 1, that is if we have only one digit, we can form 10 raised to 1 minus 1, which is 9. The last digit of the decimal number system. This is the maximum number that can be represented with n digits. What about the total combinations? If the maximum number is 9 with n equals 1, how many numbers do we have in all? We know that the decimal numbers has 10 digits, starting from 0 to 9, where 0 has a definite value. 0 is a number, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 digits in total, or 10 numbers, 10 combinations. So if n equals 1, it goes from 0 to 9, which is 10 numbers. So if n equals 2, it goes from 0 to 99. This equals to 100 numbers, or 10 raised to 2. If n equals 3, it goes from 0 to 999, which is equals to 1000 numbers, which is 10 raised to 3. And if n equals 4, it goes from 0 to 9999, which is actually equals to 10,000, and this is equals to 10 raised to 4. So the total possible combination, the total numbers that can be made with n digits is 10 raised to n. And to get the maximum number, we subtract 1 from it because we include 0 in all of those combinations. Try this yourself.